Hello mathematicians, we will see another interesting problem asked in CSAR June 2014, question 29. So this problem is about the cardinality of the sets. Okay, so in this video going to be little bit lengthier than the usual because I'm going to explain many things about the cardinality and bijections, countable set, uncountable sets, and Alaf-Knot, continuum hypothesis. So these are all very important concepts for exam. In this one video, I try to cover as much as possible. So please try to watch this video completely, and you will get a good idea of countable, uncountable sets and cardinality and how to calculate the cardinality of various sets. For example, here they are asking the cardinality of constant function, polynomial functions, continuous functions. So similar question, whatever they asked, you can do it with the help of this video. Okay, so let's start. Let's just read the question briefly to understand what we are dealing with. So consider the following sets of functions on R. Okay. So first taking W is set of all constant functions on R. X is set of all polynomial functions on R. Basically it is set of all polynomials over R. Y is set of all continuous functions over R. So it is a continuous function from R to R. And Z is set of all functions. So there is no continuity requirement. It is all functions from R to R. So we are given four sets. The question is which of these sets has a cardinality same as R? Okay. So R has certain cardinality. Now we are given four sets. We are asked to find which of these sets has cardinality same as cardinality of R. Okay, there are four options. So we'll come to the option later. First we try to understand the cardinality of these four sets. Okay. Now when do we say two sets have the same cardinality? So two sets A and B are said to have the same cardinality if there exists a bijection between them. Okay. If there is a bijection F from A to B, then we say A and B have the same cardinality. So now we come to the first option, first set. W contains set of all constant functions on R. Question is whether this set W and R has same cardinality. So we have to find a bijection between W and R, then they have the same cardinality. Let's see what is a bijection. So W set of all constant functions. So let's put some notations. So I take a arbitrary alpha belongs to R. I define f alpha. It is a function corresponds to this number alpha from R to R defined by f alpha of x equal to alpha for all x belongs to R. So basically f alpha is nothing but the constant function alpha. Okay. Now W contains all the constant functions. So notationally we can write W as set of all f of alpha such that alpha belongs to R. Okay. So W contains all the constant functions. So all the constant function means for each real number there is a constant function that we are denoted by f alpha. Therefore W can be written like this. Now from the way it is W is constructed, we are seeing it clearly. For each real number alpha there is a constant function. Conversely, given a constant function, we know what is the constant. So that is the bijection between W and R. So we write it down rigorously. Define a function phi from W to R that takes in W I take a function f of alpha and I send it to alpha. Okay. Then we can verify that this phi is a bijection. Okay, so you have to verify that well defined as 1 1 and 2. So they are all just comes out naturally, nothing to worry about. So it is a bijection, therefore W and R the sets have the same cardinality. Okay, let's come to the next set X. Set of polynomial functions on R. Okay, this is a little bit more trickier. So we develop some more notions, and those notions will be very helpful in solving other problems. Okay, so cardinality of the natural number is denoted by Alaf-Knot. Okay, remember this symbol is Alaf-Knot. Okay, if we say a set is countably infinite if the set has cardinality all of not. Okay, so if a set has cardinality same as cardinality of natural numbers, then we say that set is countably infinite. Okay, okay, then we have Cantor's theorem. Cantor's theorem says that there exists no onto function from a set A onto its power set. What is power set? Power set means a set of all subsets of A. Okay, subsets of A. So why Cantor's theorem is important? So please check the proof of Cantor's theorem in internet. Okay, proof in internet, it is a very interesting proof by contradiction proof is there. That's an interesting proof by method of contradiction, so please check this proof is very interesting. Okay, so Cantor's theorem says that there exists no onto function from A to power set of A. Now you see, definitely power set of A is a bigger set than A. We are saying that A and power set of A there is no onto function. So from this we can conclude that cardinality of A is strictly less than cardinality of power set of A. Why? Because they cannot have a same, these two sets cannot have same cardinality. If they have the same cardinality, there should be a bijection. But we are saying there is no onto function from here to here. But this set is a much bigger set than this set. Therefore, we have cardinality of A is strictly less than cardinality of power set of A, whatever set A is. For example, if A has is a finite set, it has n element, then power set of A will have 2 power n elements, which is much bigger compared to n. Okay, so now we apply this theorem to the case of natural numbers. We get the cardinality of power set of natural number is strictly greater than cardinality of natural number. Okay, but this cardinality of natural number is what we are denoted by all of naught. So we get cardinality of power set of n is strictly greater than all of naught. Okay, now we give one more notation, the cardinality of power set of natural numbers. So what is this? This is set of all subset of natural number. Who this cardinality of this power set is what we are denoted by 2 power all of naught. Okay. Uh, okay. Why we are denoted by 2 power all of naught? Because there is a bijection between power set of A and 0 1 power A. What is 0 1 power A? This is set of all functions from A to this set, A to 0 comma 1. So you collect all the functions from A to 0 comma 1, that this set is in bijection with the power set of A. This is a very simple fact, you can prove it, so please try to do it. Okay, now what is cardinality of 0 1 power A? That is a 2 power cardinality of A. Okay, also we know that cardinality of power set of A is 2 power cardinality of A always. Therefore, if so cardinal, what I am saying, cardinality of power set of A is 2 power cardinality of A, correct? So cardinality of what is power set of n? This is 2 power cardinality of n. This is equal to 2 power all of naught, because cardinality of n is all of naught. Okay, so for this reason cardinality of power set of n we denote it by 2 power all of naught. So sometimes similarly this set 0 1 power A is also sometimes simply denoted by 2 power A. Okay, and as we said here, there is a bijection between power set of A and 2 power A. Okay, so far we just define what is the meaning of 2 power all of naught. What is 2 power all of naught? 2 power all of naught is nothing but the cardinality of power set of n. And also what we have proved, all of naught is strictly less than all of naught is strictly less than 2 power all of naught. Why? Because this is cardinality of natural number, this is cardinality of power set of natural number, and by Cantor's theorem a set and its power set cannot have same cardinality. Therefore this number all of naught is strictly less than this number 2 power all of naught. Okay, so in case of n we have a power set of natural number and this 2 power n, they are same. So that is what we just saw here, power set of a set, and this set of all functions from A to 0 comma 1, and they are in bijection. So 0 1 power a is what we denoted by 2 power a in as a different way. Therefore power set of n and 2 power n, they are similar. By that we mean they have the same cardinality or there is a bijection between them. So we define cardinality of power set of n to be 2 power all of naught. That's what I just explained. So basically 2 power all of naught is the symbol for cardinality of power set of n. That is what we have understood in the above discussion. Now continuum hypothesis sta- states that there exists no cardinal number between all of naught and 2 power all of naught. Okay. So once you, if there is a set bigger than n, then that set should have cardinality power set of n. That is what it says. So there is no set whose cardinality is strictly less than cardinal. So there is no set A whose cardinality lies between cardinality of n and power set of n. Okay. That is what continuum hypothesis says that. So it is a hypothesis. So there is no rigorous proof for this fact. We just assume as it is a hypothesis and we work. Okay. So why? Because so you look at the numbers. 0 is a cardinal number because empty set has cardinality 0. Then 1, 2. If you go like this, you will reach all of naught. This is cardinality of natural number. After, so what are the sets that has cardinality in all of naught? So any countably infinite set has cardinality all of naught. So once you cross all of naught, you will get 2 power all of naught only. So here there is nothing in between all of naught and 2 power all of naught. That's what continuum hypothesis says. And there is something called generalized continuum hypothesis that says that now after all of naught you get 2 power all of naught. After that, so from here to here, how did we come? We take the power set of natural number, we came here. Now you take power set of this set. You take the power set of natural. Okay, let me write. So this is natural number. This cardinality of natural number is all of naught. This is cardinality of power set of n, that is 2 power all of naught. Now you take power set of n. That will give us cardinality 2 power all of naught. Okay, then there is no cardinal numbers between 2 power all of naught and 2 power all of naught. This is what generalized continuum hypothesis. Now again you can take a power set of power set of power set of n. Then this will have cardinality 2 power all of naught. Okay, and it goes like this. Okay, so now again there is no cardinality in between, that is due to generalized continuum hypothesis. So now after all of naught, next infinite cardinality is 2 power all of naught. Okay, so this 2 power all of naught, there is a one more name. This 2 power all of naught is also denoted by C, continuum. So 2 power all of naught has a name called continuum, so we denote it by C. So what are the cardinal numbers? 0, 1, 2, etc. all of naught, then 2 power all of naught. After 2 power all of naught, it is 2 power all of naught, then 2 power all of naught, and it keeps going. Okay. Now I'll say some exercises. Find a bijection between power set of n and r. Okay, therefore, so this is you can check in internet. There are many interesting bijection between power set of natural number and r. So because of this bijection, these two sets have the same cardinality. R and power set of n has the same cardinality. Therefore, what is cardinality of r? Cardinality of r equal to cardinality of power set of n. What is cardinality of power set of n? It is 2 power all of naught. There is another name for 2 power all of naught, that is C. Okay, so in the above 10 minutes, what we have proved is cardinality of R is 2 power all of naught. So in this problem, we want to find which are the sets has the cardinality same as R. So now we have proved that cardinality of R is 2 power all of naught. So now we can check out of the given sets which are have cardinality 2 power all of naught. Okay, I have one more exercise for you. Please try this. Find a bijection between open 0, 1 and R. Therefore, open 0, 1 also has cardinality 2 power all of naught. Okay. Okay, now we come to the question. X is a polynomial function on R. That is what is given. Okay, so it is a polynomial functions mean it will have a degree. So degree can be 0 to anything. 0 means it is a constant polynomial. Then degree 1, degree 2, degree can be anything large. So x contains all the polynomials over R. Therefore, it will contain all polynomials of all the degree. So now I take it as a union 0 to infinity. So first it will have degree 0 polynomial, their constant polynomial, then degree 1 polynomial, then degree 2 polynomial. I am taking union of them. Now, so if it is a degree n polynomial, it will be of this form: a naught plus a1x plus etc plus a n xn plus these coefficients are real number, and since it is a polynomial of degree n, this leading coefficient is not equal to 0. Okay, so this set x can be written like this. Now if it is a constant polynomial, so now again a polynomial can be thought of as a tuple of real numbers also. Okay, so if it is a degree 0 polynomial, it is a constant polynomial, then it will have just one entry in the tuple. If it is a degree 1 polynomial, then there will have it will have two coefficients. Degree 1 polynomial means a naught plus a1x, therefore it will have two coordinates, it will be a 2 tuple. Degree 2 polynomial, it will be 3 tuple. Degree 3 polynomial means it will have 4 tuple and so on. Okay, now if it is a constant polynomial, for n equal to 0, it is a constant polynomial means only you will have a0, therefore it is same as R. Then for n equal to 1, it is a polynomial of degree 1, a naught plus a1x, so it will have two coefficients. If you write it like this, you will have two coordinates, therefore it is R2. Then for degree 2 polynomial, you will get R3 and so on. Therefore, this set is same as R union, R2 union, R3 union, etc. etc. Okay. Now, you look at Rn. What is cardinality of Rn? Cardinality of Rn is cardinality of R into cardinality of R n times. What is cardinality of, sorry, I should write R, real numbers. So cardinality of this R is 2 power all of naught, cardinality of R is 2 power all of naught, this R is 2 power all of naught n times. Okay. Therefore, now in the cardinal arithmetic, you can just take the product like usual number. So you add the powers. So 2 power all of naught plus all of naught, there are n many all of naught. So this all of naught is cardinality of a countable set. So this is a cardinality of another countable set, like some countable set. So we add the cardinality when we take the union of the sets, right? If you take union of two sets, then you take the sum of the associated cardinality. So here I am taking finitely many all of naught means I am taking finite union of countable set. Finite union of countable set, we know that it is countable, therefore the sum of all of naught is again all of naught. So finite union of countable set is countable, even countable union of countable set is also countable. So even if you add all of naught countably infinite times, you will get again all of naught. Okay, so what we got, cardinality of R power n, we got 2 power all of naught. So R power n also has the same cardinality as R. Okay, so now for each of this R cube, R square, R cube, we can replace its cardinality. So it is a union, so we have to sum the associated cardinality. So 2 power all of naught plus 2 power all of naught plus 2 power all of naught and so on. So if you add countably, it is like countable union of countable set is countable. Similarly, if you add a countable union of sets of cardinality 2 power all of naught is also again 2 power all of naught. Okay. Therefore, 2 power all of naught plus 2 power all of naught, 2 power all of naught. If you add it again, you get 2 power all of naught. Okay. So what we got? So we get the set of all polynomial functions on an R has cardinality 2 power all of naught. Therefore, X has cardinality of R because the cardinality of R is 2 power all of naught. Okay. Okay, let's go to the next option. So before go to the next option, we look at R power infinity. So this will be needed for the next option. What is R power infinity? R power infinity means R power n means it will have n tuples. Infinity means it will have infinitely many tuples. So infinitely many tuples means basically they are sequences. Okay, if it's a sequence, it will have infinitely many terms. That can be thought of as a infinite tuple also. So r power infinity is another symbol for set of all sequences over R. So we claim that this r power infinity also has same cardinality as R. So again the same argument, r power infinity equal to cardinality of r infinitely many times. So 2 power of naught into 2 power of naught infinity many times. So you just add the powers. As I said, countable union of countable set is countable. Therefore, all of naught plus all of naught infinity many times again give all of naught. Therefore, cardinality of set of all real sequences is 2 power all of naught. Therefore, set of all real sequences also has cardinality equal to R. Okay, this is our own observation. Using this observation, we prove that the set of all continuous function on R, that will also has cardinality same as R. That is what we are going to prove. So before first we observe something about continuous function from R to R. Using that observation, we prove that the set Y also has cardinality same as R. Okay. Okay. Let f from R to R be a continuous function. First I am, so rational numbers are countably infinite. So they have cardinality of q is all of naught. Okay. So take it as an exercise and try to construct a bijection between natural number and rationals. Okay. Some kind of diagonalization kind of argument you can do. So we can enumerate the rational numbers. First rational number, like first rational number, second rational number, third rational number. So this all set of all rational numbers can be written as a sequence. Okay, now I take a irrational number. Alpha is a irrational number. Now rational numbers are dense in R. Dense means, therefore, given a any real number, there exists a sequence of rationals converging to that real number. In particular, there is a sequence of real numbers that I denoted by Rij, j equal to 1 to infinity. Okay, this sequence of rational numbers converges to alpha. Okay, so since rationals are dense, whatever real number you give, there is a rational sequence converges to that number. In particular, to alpha also, there is a rational number converging to that alpha. Now f is a continuous at the point alpha, right? So if it is a continuous function, if it is continuous at alpha, whenever xn tend to x, f of xn will tend to f of x. That is a definition of continuous function. Therefore, f of f of this sequence converges to f of alpha. Okay, that is f of alpha equal to limit n tend to infinity this sequence. Right. So from this what we are understanding is, if we know the value of the function f at the rational numbers r1, r2, etc., then at irrational points the value can be calculated. Okay. So in particular the function f is known, if f is known on irrationals, then f is known on irrationals, because on take a irrational number, there will be a rational sequence converges to that irrational, then use the continuity to find the value of the function f at the irrational. Okay, so if so f can be, the continuous function can be uniquely represented as f of r1, f of r2, f of r3, etc., because um, we just need to know the value of the function at the rationals. Irrational can be calculated. Therefore, f can be uniquely represented as a sequence. This is a sequence of real numbers. Okay, and suppose if you are taking two distinct functions, then they will give rise to two different sequences. Because if the two sequences are, if the two functions agrees on rational numbers, then it will agree on irrationals also, and then f will be g. Okay, so what we get is, if two distinct continuous functions are given, we get two distinct real sequences. Therefore, if c r comma r, if this is a set of all continuous function from r to r, for each function I am getting a real sequence. The real sequence is denoted by r power infinity. We just saw that r power infinity has cardinality same as r. Just before we saw that. Okay, for so remember that here we proved that a set of all sequences over R has cardinality 2 power of naught, which is cardinality of R. Now what we have done is uh, any continuous function we thought of as a real sequence, and this gives, therefore this gives a map from continuous function to sequence, and it is a 1 1 function. Therefore we get the cardinality of C of R comma R. Continuous function from R to R has cardinality. So if once you have a 1 1 function from here to here, this set has cardinality lesser than this set. Okay, therefore cardinality of C of R comma R less than or equal to 2 power all of naught. Okay. Now in the first option we saw that set of all set of all constant functions and set of all real numbers, they have the same cardinality, and the constant functions are continuous, right? So the CRR contains all the constant functions, and the constant functions has cardinality 2 power all of naught. Therefore so these constant functions form a subset of C of R comma R. Therefore this set will have cardinality bigger than constant functions. Therefore constant functions have cardinality 2 power all of naught. Therefore C of R has cardinality at least 2 power all of naught. So now we combining these two things, we get C of R has cardinality 2 power all of naught. C of R is the set of all continuous function R to R. That is what our given set y, set of all continuous function from R, that is our y. C of R comma R is nothing but our function y. Okay. So now we come to the, so whatever so far we have seen, all the set we have encountered have the same cardinality as R. We come to the last set. Z contains set of all functions on R. We collect all the functions from R, that is our Z. Now this set has a subset. You look at a function R to 0 comma 1. You see 0 comma 1 is a real number, 0 and 1 are real number. So if you take any function from R to 0 comma 1, that is will be a proper, it will be a proper subset of set of all functions from R to R. Okay. Now what is set of all function from R to 0 comma 1? This set is this set is what we have denoted by 2 power R, and 2 power R and power set of R are same. That is what we saw in the beginning of the lecture. Therefore, so this inside set of all functions from R to R, we can identify power set of R. Okay. Therefore, this is a subset of Z. Power set of R is a subset of Z. Therefore, cardinality of power set of R is less than or equal to cardinality of Z, because it is a subset, it is a superset. Okay. So, what is the cardinality of power set of R? R has cardinality C. C is nothing but C is the another name for 2 power all of naught. Okay. So, if R has, so this is C is cardinality of R. Then power set of R will have its 2 power all of naught, that is same as 2 power C. Okay. And since cardinality of Z is greater than or equal to cardinality of power set of R, cardinality of Z is greater than or equal to 2 power C, and 2 power C is strictly greater than C. Okay. Therefore, cardinality of Z is strictly greater than C. So, therefore, cardinality of Z cannot be equal to 2 power all of naught. Therefore, cardinality of Z is not equal to R. Okay. So, what is the correct option? So, there is a mistake in the problem. So, option 3 is what is correct. Okay. W, X, Y. All this set has cardinality same as R, and Z doesn't have the cardinality equal to R. Okay. So, I hope you understand this problem. Please go through it completely to understand things clearly. If you want me to do some particular problem, please comment below. I will do the problem. I try to do it in the very next day itself. Thank you. Have a good day.